Imagine if you could freeze time, not with a machine or a spell, but simply by watching something closely enough. Sounds insane, right? But in the quantum world, this isn't fiction, it's fact. Welcome to the Quantum Zeno Effect, where the act of observation can actually halt change itself. In everyday life, time marches on. You watch a candle, it melts. You watch someone age, they still grow older. But that's our macroscopic world, the world of large things, like people, cars, and planets. The quantum world, it's a different beast. It follows different rules. To understand the Quantum Zeno Effect, we first need to understand a few quantum basics. Superposition. Particles can exist in multiple states at once. Measurement. When you observe a quantum system, it chooses a state. Collapse, which is the act of measuring that forces that decision. The Quantum Zeno Effect happens when you measure too much, too often, and the system stops evolving altogether. The effect is named after Zeno of Ilia, an ancient Greek philosopher. He proposed strange paradoxes to show how motion might be an illusion. One of his most famous, a moving arrow is at rest at every instant of time. Meaning, if time is made of infinite moments, then at each moment, the arrow isn't moving, it's frozen. So how does motion happen at all? Fast forward to quantum physics, and something eerily similar happens. If you observe a quantum system continuously, you interrupt its evolution. It's like asking the universe every microsecond, "Are you changing yet?" And the universe responds, "Nope, still the same." This isn't just theory, it's been tested. In 1990, physicists Itano, Heinzen, Bollinger, and Wineland conducted a famous experiment. They took beryllium ions, tiny atoms, and prepared them in a state where they were about to jump from one energy level to another. But here's what they did. They kept measuring the atom's state again, and again, and again, and guess what? The atom stopped changing. Observation had frozen its evolution, just like Zeno's paradox predicted, thousands of years ago. Let me simplify. Imagine you're cooking popcorn in a microwave. Normally it pops when you leave it alone. But now imagine opening the microwave door every second to check. You interrupt the heating, and the popcorn never pops. Or picture trying to make a big decision, quitting your job, ending a relationship, but every few seconds someone asks, "Are you sure? Are you sure? Still sure?" Eventually you're paralyzed, you freeze. That's the Quantum Zeno Effect. Constantly checking prevents the process from completing. In quantum physics, change over time is linked to probability. A particle has a certain probability to jump to a new state after some time, but if we keep observing it frequently, we reset that timer, over and over, like clicking pause on every frame of a movie. So, if change is frozen, is time itself frozen? For that particle, yes. Observation acts as a control mechanism, almost like a universal remote. But there's a twist. The anti-Zeno effect. In some systems, frequent observation doesn't freeze change, it accelerates it. It's like constantly checking your phone, and every time you do, more emails appear. Or, opening the oven constantly and it bakes faster. Weird, right? Whether you get Zeno or anti-Zeno depends on how you're observing, what you're observing, and the system's coherence. Here's where it gets deep. Who or what is doing the observation? Is it a measuring device or is it us? Some interpretations suggest consciousness plays a key role in collapsing wave functions, choosing a reality. Could that mean our attention, our awareness, actually shapes the flow of time? That by watching something closely, we're not just observing reality, we're interfering with it. The Quantum Zeno Effect opens philosophical doors. Could this explain why meditation slows perception of time? Why intense focus makes moments feel longer? Could this be why some people say that time stood still during a moment of fear, or love, or realization? And in the lab, can we use this to build more stable quantum computers, or preserve quantum states by controlling how often we measure them? In our everyday world, time flows forward. Things change, evolve, decay. But deep beneath it all, at the quantum level, reality behaves like a stubborn child. If you watch it too hard, it stops playing. The Quantum Zeno Effect is proof that observation is not passive, it's powerful. In quantum physics, to see is to change, to observe is to control time. So, are you watching closely enough? Beyond Newton is not just a place, it's a question, asked at the smallest scale, where reality forgets how to behave.